parameter variation. Those kind of explanation, detailed explanation, obviously is not possible with this. For that, we need some kind of systematic way of discussion from scratch, the details analysis. But objective of this discussion is we need to give one overview. The systems of what we are using in our engineering systems, but that not necessarily that's only this phenomena only concentrated on engineering systems, many other systems also. But the engineering systems of what we are usually deal, that's also typical kind of behavior. And if we are interested to investigate why those kind of behaviors are coming, and if you understand the occurrence of those behavior, then maybe it is possible to use those behavior as a beneficial way, or to restrict or suppress, or we can say to control. Because if you understand the behavior, it is easy to suppress or to control. So for that, with a very short time, lectures may not be so interesting, but I am trying to explain based on some slides show. Title we can put within 2-3 class the nonlinear phenomena and bifurcation. So nonlinear phenomena obviously this is the English word. Nonlinear, this is some typical kind of phenomena which is coming from the nonlinear systems, which are not comes from the linear system. So what is the definition of linear systems and nonlinear system? Obviously Professor Rudra may be roughly discussed, but in addition to that, I can say you nonlinear systems it can formed by system itself, and maybe some systems also linear, but if you put some kind of feedback controller, then since the feedback controller is also nonlinear, then overall closed loop systems will become also nonlinear. From mathematically how to define nonlinear system, there is the mathematical subject how to describe the nonlinear systems. Since we are talking about the dynamical system, not static system, obviously the systems will be defined by differential equation. Maybe partial, maybe ordinary differential equation. But that differential equations will characterize the nonlinearity. So that is the mathematical subject. So what kind of, how many ways we can describe the nonlinear system in the form of a mathematical equation, that is the different subject. But we can assume now it is possible to describe. But broadly, without going too much to the mathematics, if you go if you classify the nonlinear system, then broadly I can say the nonlinear systems can be classified in broadly 2 groups. One we are calling the smooth system, smooth nonlinear system. What is the smooth nonlinear systems? If some nonlinearity in the describing functions, means governing differential equation, is there is a no such kind of signum or switching or any kind of sudden transitions is there. Some mathematical function which describe the sudden transitions, t is equal to t, just t greater than 0 plus, one dynamical behaviors and 0 minus another dynamical behaviors. Sudden transitions, if it is not there, so any governing equation which is not of sudden mathematical functions of sudden transition, then so we will say this is the smooth differential equations of smooth nonlinear systems. Meaning we can say in terms of algebraical equations, if you think, so when functions which has a continuous as well as derivable at each and every point, so that is smooth system. If it is a continuous but not derivable each and every point, then Taylor expansion is not possible at that transition point. So that times we call this is the non-smooth nonlinear system. So since it is a nonlinear system, then some peculiarity will come, we will see that. And the peculiarity and the transitions between one phenomena to another phenomena may differ if you consider smooth nonlinear systems and non-smooth nonlinear systems. And some systems also exist where there is a combination of smooth and non-smooth. So sometimes the transitions is happening smooth to non-smooth, and sometimes transitions is happening in smooth region itself. So that's why the phenomena which is coming from the nonlinear systems is very difficult to understand unless people are not investigating very deeply. Now I am giving an example, but that's again I am saying that may not be. We may not consider this example. Many other examples is there. You can take the example from chemical engineering, biological systems. We can electronic system, communication system. So more or less every systems are more or less nonlinear if you accurately model that. But if we are electrical engineers, so if you take one electrical system, maybe I have taken one electrical systems people are looking for. So the systems we can say renewable energy system. So which consists of some renewable generation. That's here what I can show you some wind generation system. Some solar systems which is maybe in some geographical location it is situated, some rooftop solar system, and along with that some centralized our conventional power plant, and obviously we have some kind of transmission system. So we are using, and also some kind of load which may be our domestic load like load or others, and which may be our sorry.
No, sir, please continue.
I'm not getting.
Sir, please continue. Yours just accidentally turned on his microphone. Please continue.
So, so different kind of load. So these kind of systems we are looking for being an electrical engineer. So, and those systems, if you see the classical way of analysis or textbook, then they are not dealing so much the nonlinear phenomena, nonlinear behaviors. They are not modeling those systems in terms of nonlinear equations and all, dynamical equations and all. But now the question is coming, and they are really those systems are not nonlinear, or those are linear, or we are doing the linear analysis for some kind of simplification or easy to understand or easy to deal, or something is hidden so we are not bothering those things. So if you consider, so we can extract more or not. So those are the questions are coming, and if you understand that one fully, then those understanding can be useful for better control or cost optimizations or better design, and all the issues are coming. So from that perspective, maybe switching over here and there, and suddenly we'll conclude something. So then suddenly is coming what is the nonlinear phenomena. So sometimes when we are talking about nonlinear phenomena, people are normally expressing those phenomena in terms of phase plane or state plane. Obviously, Professor Rudra already, I hope, they discussed what is the phase plane. So I'm just saying into this way, the phase plane maybe we can define into this way some kind of pictorial view of a where axis is actually the state vectors. So or state variable. So when you are presenting some kind of system behavior in the form of some diagram where two axes variable, we are calling the system's behavior represented in terms of phase plane or state plane. But if you are observing the system behavior in terms of one time axis and another axis is your state variable, then we are talking as a waveform. So now question is, since I am intentionally not showing those kind of waveform, because waveform we are used to see. So if you little bit realize some waveform where x-axis is the time axis and y-axis is the any of the state variable, and waveform's nature is periodic nature. Periodic waveform, maybe the sinusoidal, maybe triangular, maybe square or whatever maybe. And I am plotting some kind of with respect to time, which is giving some kind of periodic waveform. And another state variable also I am plotting with respect to time, it is giving another periodic waveform, may not be exactly with the same with the previous one. And then I am plotting with these two state variable x1 and x2 freezing the time, means one axis is x1 and another axis is x2. Then I will see different kind of patterns. That's the xy plane, the xy plane behaviors. That's actually the phase plane. So now this is also one system's behavior of a phase plane. So now if you have, that's everybody, I think this is the MTech class, everybody already observed this one. If you have sinusoidal one waveform, you are putting in its CROX channel, and with some phase shift, if you have putting in Y channel and XY plot we are observing, then we will get one kind of cycle. May not be circle, but we will get one kind of cycle. So that is also a phase plane diagram, but phase plane diagram giving one kind of cycle. So those kind of things also one steady state behavior. So now, if the phase plane is not forming one cycle, it is forming very randomly and very what you can say unpredictably, and forming one picture, and the pictures looks like this. So then, what kind of behavior it is at steady state? So since I am coming to the steady state now, then I am little bit deviating from the linear to non-linear, and I am saying in linear systems, so what we wish to get. So linear systems at steady state tends to infinity if your dx by dt, which is the dynamical equation, left hand side equations may be first order, or if you are higher order, then we will get maybe d2, d3, x by dt square or whatever maybe. Then at is equal to 0, if you put and calculate the the value of the states, that will give you the equilibrium point. We will get the equilibrium point. So if the solution is exist by equating 0, then we are calling the existence of the equilibrium point. Equilibrium point exists. But that does not mean that the equilibrium point will be stable or equilibrium point will be unstable. We can only assure by is equal to 0, if you're getting some kind of solution of x, then we can say the existence of equilibrium point. But for stability of the equilibrium point, we have to go further. That's the around the equilibrium point, we need to calculate the eigenvalues and all this stuff, and we need to be check the natures of the eigenvalues. But what my interest is that if we considering the linear systems, then we are getting one equilibrium point. First, the equilibrium point is the steady state value. And that equilibrium point may be unstable, then we can say that the unstable systems equilibrium point is stable, then we can the stable systems. And how the equilibrium point evolving with from the 0 value, then we are calling the evolutions of the system. But in nonlinear systems, there may not be equilibrium point. There may be other steady state behavior. One just now what I told that we can get conformations of one cycle. That's we are calling the limit cycle. In similar case, the limit cycles may be unstable and limit cycles may be also stable. But apart from the limit cycle, we may get in state space some peculiar kind of trajectory evolution, which is not equilibrium point, just a point, which is not repeating and following a same path in cyclic manner ever and ever, which is very randomly rotating and evolving, but it is bounded. Bounded means it is going to infinity. So that's actually the peculiar one behaviors we people are observing in nonlinear systems. So it is not repeating, it is not converging to one point. It is randomly it is traveling, but it is bounded. It is not unbounded, but it is unpredictable. We cannot predict which path previously it travels and now which path it will travel and next which path it will travel. We cannot predict that. So, and these kind of bounded aperiodic kind of evolutions also depends upon the initial condition. Because slightly I am changing some initial conditions, then we will see totally different kind of trajectory evolution. But in steady state, it is bounded. It is not exactly will be repeating the previous one. So these kind of peculiar phenomena people are actually terming as a chaos. So literally, if you say that what is the definition of chaos? Chaos is a nonlinear phenomena which is sensitive to the initial condition, and it is unpredictable and bounded. So if you change the initial condition, the trajectory evolutions will be totally, it will be changed, and but steady state it will be bounded. So those kind of behaviors also we may observe in nonlinear systems. Apart from that, since we talk about the limit cycle, so that's also we can observe in one nonlinear systems which are not observing in a linear systems. Linear systems maybe at the slides, what is the initial positions, what I am showing, maybe it will be, it converges to some point. But in nonlinear system at steady states, it will show the sustained oscillations and that's oscillations, and it will be stable. That's limit cycle will be stable, meaning if we change the limit cycle little bit, it will converge to there. What is the definitions of the stability? If you slightly part out from his positions, then again it will converge to the original one. So the purpose of this putting these figures is that I have in a red dot what I am putting is the fixed point. Fixed point actually one terms in discretized versions people are saying. Fixed point is
Excuse me, sir.
equivalent.
Sir, are you presenting something?
Slide I'm showing.
Sir, actually in my window I cannot see the slide. Have you shared it?
Oh, so far you have not seen the slide.
Yes, actually that is why I thought that means you are going to present it. But then when you said red dot, then I got confirmation that the slide got shared.
Okay, then I need to be little bit, I need to repeat. Now it is visible.
Yes, sir. Yes, sir. It's
So,
clear.
okay, now I'm quickly from previous maybe few discussion. I'm the first I told the renewable applications, the plant applications. I told the pictures is this, which consists of some wind generation, which consists of some solar generation, which consists of our residential building, some load. Those we are looking for. And people are designing, modeling, controlling those kind of systems, but people are not looking at the nonlinear behaviors as well as the nonlinear modeling of the systems. Already I told verbally, but picture. Next slide, the maximum time what I spent, the chaotic behaviors I told, what I told the verbally, this is the pictures I am showing the chaotic behaviors. Now I think the students are also can view that.
Yes, sir. Yes, sir. It's clearly
Yeah.
visible.
So this is actually, I spend more maximum time there. What is the definition of chaotic behavior? It is very peculiar. This is fully unpredictable. It is the orbit, it's not repeating, following the same path. But one observations we are getting, it is bounded. It is not repeating, but it is not unbounded. So that is we can say characteristics of the chaotic behaviors, and chaotic behavior is also one steady state behaviors of a nonlinear system. So and the definition of chaotic behaviors also I told that it is very sensitive to initial conditions and it will not be repetitive and it will be bounded, and which is slightly different from the noise. And noise also, it is apparently it will be looks like chaotic kind of system, but noise is fully unpredictable. But chaotic orbit is predictable if we follow exactly the same parameters as well as the initial condition of the previous one. Means what I am trying to say is that I am taking one systems with some parameters, value and initial conditions and evolutions I am observing and phase plane I am plotting. I am getting this kind of one phase plane. And after one day, I am evolving the same system with same parameters, same condition and same initial condition. Then exactly same things I will get. That's why people are saying it is unpredictable but deterministic. We can determine if you follow exactly the same value and same initial condition, which is not possible for noise. Today, one exactly the same experiment, the noise behaviors I am capturing, and after one day, same value noise behaviors I am capturing, that will not be same. And that is the difference, because noise is unpredictable. Chaos is unpredictable but deterministic. Noise is non-deterministic. So this is the some kind of pictorial view of chaotic attractor, because at steady states the behaviors we are normally used to say the equilibrium point for a linear system, and equilibrium point it is stable. We can say the equilibrium points also as an attractor. It will attract, and chaos also one attractor. But that attractor is particularly is coming in nonlinear system. Another as a attractor may be possible in nonlinear systems, as I told, this is the limit cycle. So means the sustained oscillation in terms of waveform or a closed cycle in terms of phase plane or state plane. That's also may come in a nonlinear system. And second is another peculiar behaviors may come to nonlinear systems that we call torus or quasi-periodic orbit. So the quasi-periodic orbit is what? Quasi-periodic orbit is sometimes those kind of oscillations very frequently we have seen our system. What is that? Suppose we have one sinusoidal waveform, right? And another sinusoidal waveform with high frequency, maybe one sinusoidal waveform of 5 Hz and another sinusoidal waveform of maybe 50 Hz, and that sinusoidal waveform superimposed on the first sinusoidal waveform, slow oscillatory waveform. So if these two waveforms, if superimposed, then you can visualize some high frequency sinusoidal waveform and which is evolving as a low sinusoidal waveform. So those kind of also oscillations also very frequently we have observed in our electronic system. But if we don't look into this manner in a waveform manner, if we look those kind of dynamical behavior in terms of phase plane or state plane manners, then pictures I will observe. I will observe one torus kind of pictures. Torus is a geometrical shape. Means as a physical example, you can say you can consider it a cycle tube. So if you put some air in a cycle tube, the shape what we will get, that is the torus shape, where we will get the dominant two frequency of evolution. So one frequency of evolution, say here I am showing as a red color. So one orbit can roam into this way, and another evolutions I am showing as a blue color. So those kind of oscillations may come. And just in the previous examples, if you just couple with these, then I can say you the blue color oscillations actually is the first frequency oscillation sinusoidal, and one times it is rounding, means the red colors means the slow frequency oscillation. So this is two-dimensional torus. And if this torus itself it is rotating and horizontally or vertically it is rotating, then another frequency also will come. That's we call the three-frequency torus. So that's also may come. So some dynamical systems which has some kind of inherently frequency of oscillations which is 2 or more than 2, then those kind of steady state behaviors also we will observe, and those things we are calling the torus structure. And that's also another basic steady state behaviors of nonlinear systems which are normally which are not happening in a linear system. By that also in previous discussions, as I told this, so there is a possibility of then all the attractors which are happening in a linear nonlinear systems, that is the equilibrium point or fixed point, that is limit cycle, torus, that is chaos, those may be stable and unstable. So then the question is that torus instability of torus means what? Instability of limit cycle means what? Instability of chaotic means of what? That's also we can explain, and we can also say. But roughly we can say torus instability means torus puncture. We are saying this torus puncture means orbit will not be on the surface of the torus, roaming on the cycle tube. So how long he is roaming on the cycle tube, whatever may be the evolution, we can say the end steady state behavior is on quasi-periodic behaviors or torus structure behaviors, because how he is roaming on the cycle tube not matters, but he is on the cycle tube. But once it is cycle tube, we will say the torus structure has been destroyed. So that time the torus is actually loses the instability. And many other issues are also there. As I told this is I'm giving some kind of brief overview. So if the two frequency torus we are talking, two frequencies locked, means F1, if you are talking one frequency is F1, another frequency is F2, and F1 by F2 each we can you can define by integer fractions 1 by 5. And then so what will going to be happen, and if it is a irrational, then so what will going to be happen. So those are the detailed dynamical behaviors that we are not discussing today, or may not discuss at present. So locking mode, unlocking mode, and all these things are there. So borrowing that, we can say here also we can investigate the stability of the limit cycle, stability of the torus structures, and all these also we can mathematically we can also characterize. And then we are coming to some kind of is nice interesting diagrams people are looking for. So far what I am interested to say is that there is something different, fundamentally different things is happening in knowledge.
Sir, one small doubt in that toroid structure where you said that if that point leaves the toroidal structure, then it will become unstable. So, are you talking about that the limit cycle is becoming unstable,
No,
or the equilibrium point is becoming?
No. This is not the question of limit cycle and question of equilibrium point. Limit cycle is the another behaviors of the nonlinear systems. Another one kind of attractor. Equilibrium point is one kind of attractor. So the category 1 is attractor is equilibrium point. Category 2 is limit cycle. Category 3 is torus. Category 4 is the chaos. Because I'm able to guess where is the problem is happening. Limit cycle is one frequency oscillation. Torus is two frequency oscillation.
Yes,
Torus
sir, and the point of intersection of those two frequencies, what is that point denoting, sir?
I'm not getting.
Sir, you have showed that red circle and one blue curve, right? So, sir, that point of intersection of those two, where you have pointed that blue dot C1, C2, and C3, what are those points representing, sir?
No. What I'm just here. Those points. So what is the significance of those? We can discuss in later on. But what my objective is that how many ways of evolutions will be going to be happen. So never this is the point dot is a different meaning. One and suppose you are just visualize one cycle tube structure, and then question is the one ant is roaming on the cycle tube structure, and since how this way it can roam. If two ants is roaming, then there is a possible of collision. I'm not talking about that. I'm talking about the one ant is roaming on the cycle tubes. So how many ways he can roam? He can roam. He can move around the larger periphery. He can travel along the blue periphery, and then there is a different way of each movement we will get. But if your questions maybe is coming to that side, if there is a two ants is coming, and possibility of collision is not meaning that is equilibrium point.
Okay, sir.
So I am saying the possibility of evolution in state space. So this is one diagram. What it is saying, things what we can roughly what we can understand is that in nonlinear systems there is a possibility of equilibrium point. The nonlinear system there is a possibility of limit cycle. Nonlinear system, there is a possibility of torus structure or quasi-periodic oscillation. Nonlinear systems, there is a possibility of chaotic orbit. So, and there is a possibility of all these in a single nonlinear system. And but some condition is there. If the dynamical system, nonlinear dynamical systems order is less, then normally is torus structure is not coming. So if it is the system's dimension is more than 3, order of the system is more than 3 and nonlinear, then all these structures, all these steady state behaviors may come. And if you change the little bit the parameters, then so one parameter system is showing a nice equilibrium behaviors at steady state. Another parameters we are saying in steady state is it is showing the sustained oscillation. Another time we are saying it is torus structures, means sustained oscillation, and on top of that some kind of another high frequency oscillation. So another times it is very random kind of oscillation. So, but then suddenly I'm changing little bit the system behavior, system parameters, and observing the system behaviors and those kind of typical behaviors what I am observing, and then I'm little bit confused what the systems actually is showing or saying. Sometimes it is showing this very nice regular behavior, sometimes very aperiodic behavior, sometimes semi-regular kind of behavior. So it is the behaviors is giving us some kind of misleading information. So it is, I'm confused about the systems what it is showing. But to properly investigate that, people or scientists are actually formulated on procedures. How then I can understand the system behaviors under a parameters region or parameter variation. That parameters may be your system parameters, that parameters may be your control parameters. But any kind of parameters, if you change from extreme lower limit to extreme higher limit, then what possible or possibility of system behaviors it can show. So those kind of behaviors or diagrams, people are saying the bifurcation diagram. How the systems actually bifurcating. Bifurcations here is not mean that two. Bifurcations here meaning as the behavioral change, the characteristical change is happening under at what parameter value. So if I'm then continuously I'm observing the system behaviors under parameter variation and then observing at what point systems actually changing its behaviors, not changing its magnitude, changing its behavior, its phenomena. So that's actually one diagram. Actually, people are showing the bifurcation diagram. So people are people are saying that the panoramic view of system behavior under parameter variation. System behavior, that is the bifurcation diagram. Bifurcation is not is mean by two. You can say this is the bifurcation had to happen, but that two is not the bifurcation due to this two. Bifurcation is meaning here suddenly so one orbit was there which is the equilibrium point, that's why fixed point. But suddenly is the two orbits, suddenly two oscillations is coming. So that's why at this point, so that is the bifurcation point. So what is this diagram? How people have plotted and those things again we need some kind of classes. How we can plot that. What exactly it is actually saying, why this is 2, why this is not 3, is there possibly there is a 4 or 5 or 6 or whatever maybe. So those details things also we can say afterward when we go more details, maybe in some next semesters we have some dedicated course on this topic. But roughly I can say you the bifurcations, the pathways. Pathways means how the fixed point is suddenly landing to the chaotic orbit, which is the shaded kind of regions, and in between we are getting some kind of window. There is a black, what I was saying, the suddenly chaotic orbit destroyed, and then again chaotic is merged, emerged. So why those things is happening, all the scientific and mathematical explanation exist. But I can share you based on the literature or based on the today's investigation, the pathways of the chaotic orbit from a fixed point of nonlinear systems may not happen in an infinite way. The pathways is also defined. One pathway is the period doubling cascade. Period doubling means first we will get one, and then we will get two oscillations, then we will get four oscillations, and then eight oscillations, then and so on and so forth. The one way of periodic or equilibrium point will destroy its stability and ultimately converts to the chaos. In this way, we are calling period doubling cascading bifurcation. Another we call the chaos generation through quasi-periodic orbit. The chaos generation through quasi-periodic orbit means suddenly we will not get the limit cycle 2, suddenly we will get the periodic equilibrium point, and suddenly we will get the torus formation, and then we will get torus destruction. So that's also another formulations people has observed. And the structure of the bifurcation diagram, how it is looks, that look will also be differ. If your nonlinear systems is following the smooth nonlinearity, or it is following non-smooth nonlinearity. If it is a following non-smooth nonlinearity, the structure of the bifurcation diagram also will be changed. The pathways of chaos generations also. So those investigation people has already been done, and now it's an advanced textbook subject. So, but now the question is what I have started and what I am going to finish is that why those things are necessary to study for being an electrical engineer. Because as I am saying, some application is very crucial to study, and more or less in all domain it is there. And I am showing one bifurcation diagram, which is in my power electronic system, simple one boost converter under current mode control logic, and widely using, people are now using in many applications. Even your mobile phones also, Texas Instrument is making the ICs of these converters and putting. And those kind of systems also showing those kind of peculiar behaviors, and if you change the parameters, they have changed the output load. So if we change the parameters, what we have observed is that first fixed point, then period doubling, and period 4, then so this is the shaded kind of region, is chaotic orbit, and all these stuffs are coming. And normal power electronics people are not analyzing those kind of behaviors with a classical using classical analysis, and it is not possible to analyze using the classical method. So we need some kind of advanced analysis technique, and we also need some kind of concept of nonlinear dynamics to understand why those things are happening. And if you are able to understand that, obviously people understood this one for the buck converter, for the boost converter current mode control, but many other systems people did not understand. So if we understand this one properly, then we can go for suppressions, as I told, we can go for control, or we can purposefully use the systems in that domain as a beneficial way. So with that, I will conclude. But later on, I can just giving some. These are not just like a story. What I am saying, these are based on strong concept, strong mathematical foundation, and it is the pictures is looks like a painting, not like that. So some mathematics is there. We can explain those things, what I am interested to say. And yeah, with that, I will finish.
Okay, thank you, sir. And the students, please note that Professor Maity, we are very fortunate to have him among us, and he's one of the means without discrediting anyone. I would like to say that he's one of the best teacher that we have in our department. So, if you are interested in joining his research, means the I was having two objectives. When I invited Professor Maity to deliver this talk, I was having two objectives to introduce. First of all, this is not my research area, so I am not the right person to deliver a lecture on this. And the bigger goal, the second objective was like to introduce you the cutting edge technology that even you can see at your sir has still shared that present circuit on your screen. So if you are interested, really interested to pursue a research that will be contributory in nature, not a mere translational research that is just means we conduct to publish paper and something. You are interested to contribute, then you may also search some literature. You can also means email sir to his official email ID for means finding the right way to pursue research on this particular topic. And if you are interested, then there is a lot of scope of analysis is also there. That is also doing a very good, or I can say a very versatile setup of hardware is also present in SAT's laboratory. But for the time being, as you people are at your home, you can also carry out analysis by yourself. And I think means had I been there at your stage, I would have means not given a second thought to means avail this opportunity to join with Professor Maity. So I request you to means stay in touch with him, and if possible, try to find out the means obviously he cannot entertain you. And if you means the idea of pursuing research is that if you get stuck at certain point, you have to figure it out that how to solve. It is not like that if you get stuck and you run to your teacher. It is not like that nursery level, school level kid treatment. So you that if possible, means if you are really interested, join with sir and send him mail. If he finds your mail good enough, then you will answer and you will means entertain you, and you will also get a scope to means carry out research in a very dynamic field. So that's all. Thank you, sir. Okay, so I'm going to save this record.